Solve. The first thing we need to do is make all the angle measures the same. Currently, some of the angle measures are 2x and others are x. In blue, I have written the double angle formula for the sine of 2x, and in green, I wrote the double angle formulas of cosine of 2x. There is only one option for the sine of 2x. Since there is only one option for the sine of 2x, I'll make the substitution for sine of 2x, 2 sine x cosine x. I still need to decide what I want to substitute in for cosine of 2x. Simplifying the left side a little bit more might help me figure out which substitution I want to make for cosine of 2x. If possible, we would like to make a substitution that would result in the equation having all sine or all cosine. This is not going to work because the left side already has a mix of sine and cosine. The reality is sometimes you have to guess one, try it, and if it doesn't work, abandon and try another one. We can at least make a good guess. The term on the left side has a cosine squared of x, so I might want to go with one of the top two green equations. The left side does not have sine squared of x, so I'm going to go with the middle of the green. Now that I've substituted 2 cosine squared x minus 1 for cosine of 2x, I need to distribute sine of x. Next, I will move all the terms to the same side. When I subtract 2 sine x cosine squared x, those terms drop out of both sides. The only thing remaining is negative sine x. I would like a positive coefficient, so I divide both sides by negative 1. To solve 0 equals sine x, go to the unit circle and find the angle measures where the y-coordinate is equal to 0. This happens at two angle measures, x equals 0 and x equals pi. The directions for this problem said just solve, not solve on the interval 0 to 2 pi. So we need to create equations that generate all solutions. Answers to sine, cosine, secant, and cosecant all repeat every 2 pi. So we can add or subtract 2 pi to these numbers as many times as we want, and we will get additional solutions to the equation. The notation to do that is to add 2 pi k. Ordinarily, these two equations would be my final answer. But these equations can be simplified. If k is an integer, then we can find additional answers by substituting in negative 1, 0, 1, 2, 3, etc. If I substitute negative 1 into this equation, then I will get 0 plus 2 pi times negative 1, which is negative 2 pi. If I substitute 0 in for k, I will get 0. If I substitute 1 in for k, I will get 2 pi. If I substitute 2 in for k, I will get 4 pi, and so on. Here are a few angle measures this equation is generating. Let's list a few of the answers that this equation generates. If we substitute k with negative 1, we will get negative pi. If I let k equal 0, I would get pi plus 2 pi times 0 and get pi. If I let k equal 1, we would have pi plus 2 pi times 1, giving us 3 pi. And if I let k equal 2, we would have pi plus 2 pi times 2, which is 5 pi, and so on. Substituting a handful of integers for k and finding a few specific angle measures that are answers to the equation is a good way to decide if the equations could be simplified. If equations can be simplified, the first thing we look for is if one of the equations is creating duplicate answers. And if it is, then we leave out that equation. Each one of these equations is generating a unique set of answers. So we wouldn't want to eliminate one of these equations. However, if we merge the answers from both lists and write one list that contains all of the answers to this equation, we see a pattern emerge. We could write one equation that describes this pattern. The equation x equals k pi would generate all of these solutions. If I let k equal -2, I would get -2 pi, and k equals -1, -pi, and k equals 0, 0, k equals 1 pi, k equals 2, 2 pi, and so on. The best final answer would be the one equation x equals k pi, such that k is an element of the integers. If you notice in the back of the book, they would use x equals n pi, and they just define the n specifically as 0 plus or minus 1 and 2, rather than saying integers. Don't get too caught up in simplifying the equations. If you can at least get to equations that generate all of the answers, you've done an excellent job. So if your final answer was the two equations that I circled, I would give you full credit on a test. Simplifying the equations to one equation would be a great bonus.